So in this video, I am going to present a theorem which I believe is it's quite important, and it's also a little bit confusing sometimes for students who are entering first year university from high school, especially because it's taught a little bit differently at a high school level. So let me just really quickly go over the theorem first. It says let a be any real number, and then let f be a function that is defined everywhere except maybe at a. And we're saying that limit as x approaches a, that if limit as x approaches a of f of x is infinity, then that is the same thing as the limit not existing. Okay, it's not exactly the same thing. What I'm saying is that if the limit is infinity, that implies that the limit does not exist. The opposite is not true. Um, I mean, if the limit does not exist, that does not mean that the limit has to be infinity. It can be negative infinity. I mean, it cannot exist for some other reason, like the one-sided limits are not equal, or maybe if you're taking a limit at infinity, then maybe the issue is that the function oscillates as it approaches infinity or even a particular number. So, I mean, for example, there's a very famous function. I'm going to leave it up to you to find out what function that is. That basically starts to oscillate faster and faster between -1 and 1 as it approaches 0. So that would be another way for the limit to not exist. It's not because the one-sided limits are not equal, it's simply because the function oscillates between -1 and 1. So it doesn't approach a single real number as the function or as x approaches 0. Okay, so that's the theorem. One thing I would like to emphasize is that we do not actually require this function to be defined for every real number. It's typically only defined. It only needs to be defined close to a. But I'm just going to look over that detail for now. It's not really relevant to the actual proof. It's not going to change the proof at all. Yeah, so it doesn't really make that big of a difference. Okay, so at this point, I would ask you to pause the videos and see if you can prove this theorem on your own. One hint that I will give you is that you will have to use the epsilon delta definition of what it means for a limit to be infinity or what it means for a limit to not exist. So the epsilon delta definition will be required. You can prove this theorem intuitively, like you can convince yourself that this theorem is intuitively true, but as far as a rigorous proof is concerned, an epsilon delta definition will be necessary. So once again, see if you can solve this question on your own. So by now, I hope you've attempted this question on your own. I'm going to, the proof for this is actually quite straightforward once you get like, I mean, if you've done a bunch of epsilon delta proofs already, I'm pretty sure you'll find this to be quite straightforward. So yep, let's begin with the proof. Okay, so once again, whenever I start my proof, I pretty much like to define every variable that I'm going to be using in the rest of the proof, or most of the variables that I'll be using in the proof. So in this case, I'll be using a. So I'm just gonna say let a be any real number, and I'm also gonna use f. So I'm gonna say let f be a function. Okay, I'm gonna actually correct this. I'm gonna say let f be a function defined close to a, or the rigorous way of saying is defined on an interval centered at a, except possibly at a. So we do not require the function to be defined at a. So except possibly at a. Okay. So the next thing is I'm going to assume that the limit as x approaches a of f of x is infinity. So assume limit as x approaches a of f of x is infinity, and this is where the epsilon delta definition is going to come in. So what does it mean for a limit to be infinity in an epsilon delta definition? It's basically written as for every real number m, there exists delta. I'm going to call this delta prime for now. There exists a delta prime greater than 0 such that for every x, or for every real number x, if 0 is less than the absolute value of x minus a, which is less than delta prime, then the absolute value of f of x, or you don't need the absolute value anymore, f of x is greater than m. So this is basically what it means for a limit of a function to be infinity, especially if you're writing out an epsilon delta proof. You need to know this definition. Otherwise, this proof is just going to be really, really hard. Okay, so now once I've written this definition down, the next thing I'm going to do is basically state what I want to prove. So I want to show limit as x approaches a of f of x does not exist. So what does this mean? What does it mean for a limit to not exist? Well, the epsilon delta definition is as follows. For every real number, there exists an epsilon greater than 0, such that for every delta greater than 0, there exists an x in the set of real numbers, such that if 0 is less than the absolute value of x minus a, which is less than delta. So this is true, and I also want one other thing to be true here. Hold on a sec, let me just resize this. Okay, and I also want the absolute value of f of x minus L to be greater than epsilon. Okay, so some of you might be wondering where this is coming from. If you know what the definition is for a limit, like what's the rigorous definition for a limit as x approaches a of f of x to exist, this is basically just a negation of that. So I mean, if a limit exists, then the rigorous definition says that there exists a real number L such that for every epsilon greater than 0, there exists a delta greater than 0 such that for every x that is in the real numbers, if 0 is less than the absolute value of x minus a, which is less than delta, then the absolute value of f of x minus L is less than or equal to epsilon. So this is basically just a negation of that. So now this is basically, so far this is basically just the setup of the proof. This is typically what we always do whenever we are proving, or whenever we are writing down a rigorous proof. This is the framework within which I'm going to write my proof. Okay, so let's begin. This is what I want to prove. So first of all, I'm just going to say let L be any real number, because my proof needs to work for any real number L. Now I need to state what epsilon I'm using, because it says there exists an epsilon, so I need to state what epsilon I'm using. In this case, it doesn't actually matter what epsilon you use, so I'm just gonna say let epsilon be 1, for example. You can say like let epsilon be any arbitrary real number, let epsilon be 2, 3, 4, as long as it's a positive real number, it's fine. So I'm say let epsilon be equal to 1, it doesn't matter anyway. And now what I'm going to do is I'm going to say, now notice this is probably one of the most important parts of the proof. Notice what you want to show. One of the things that you want to show is that the absolute value of f of x minus L is greater than epsilon. And what do you already know? You know that f of x is greater than m. So I mean, because this is a part of our assumption, this is what we want to show. So there needs to be, because of course we need to use the assumption to prove this, so there has to be some connection between the assumption and what we want to show. So in this case, notice that the absolute value of f of x minus L is greater than epsilon can essentially be written out like this as well. F of x is greater than L plus epsilon, or f of x is less than L minus epsilon. If one of these two conditions are met, then we can conclude that the absolute value of f of x minus L is greater than epsilon. And in this case, what I see is I'm basically going to ignore this part. If you see this part, it looks quite like this part right here, that f of x is greater than m, except that instead of m, I now have L plus epsilon. And that is what I'm going to do now. I mean, I'm going to correct this by saying I use m equals L plus 1, which by the way is a real number. So I'm just gonna state that it's a real number. I use m equals L plus 1, and let's just call this first definition 1. Let's say in 1. Now, why can I do that? Because notice that this first definition, it's true for every real number. So if it's true for every real number, it also has to be true for the real number of my choice, and that in this case is L plus 1, which is the same thing as L plus epsilon. So I mean, I can even just write L plus epsilon over here. Doesn't make a difference. L plus epsilon and 1, and then I know then now there must exist a delta prime. This is once again from definition 1. there must exist a delta prime greater than 0 such that for every x in the real numbers, if 0 is less than the absolute value of x minus a, which is less than delta prime, then f of x is greater than L plus epsilon. Okay, so we're done up to this point. The next thing I need to do, so once again, this is what I'm showing. I've picked my epsilon. Now I'm going to just say let delta be any real number that's greater than 0. In fact, before that, just, for the sake of it, just to be completely rigorous, let's call this 2. The idea over here is that later on in my proof, I actually want to use this delta prime over here. But if you're being completely rigorous, this delta prime is actually quantified. So I need to dequantify it first before I can use it in my proof. This is something you often overlook. It's not something, you need to be too careful about. You can actually reuse it, but if you're just being super rigorous, it's better to just state. It's just better to dequantify it first. So what I'm going to say is like let delta prime be a value which satisfies 2. So condition number 2, it satisfies condition number 2. Now let delta be anything that is greater than 0. So this is that part of my proof. And now I need to pick an x. Now this is the part that is probably the hardest one in this entire proof. I've seen a lot of students get confused at this point. Now what you need to do is you need to pick a real number x, and the choice of the real number x or this real number is actually very important, because through this choice you actually need to satisfy 2 different conditions. One condition you need to satisfy is this one right here, that the real number x you pick has to be within delta of a, and at the same time it also has to be within delta prime of a. So I need to make sure that both of these conditions are satisfied simultaneously, and the way to do that, the way, perhaps it's not the only way to do that, but one of the ways is as follows. I'm going to say take x, or let x be a real number, such that 0 is less than the absolute value of x minus a, which is less than, and this is why I dequantify delta prime, because I'll use it over here. It's less than minimum of delta prime and delta. So why does this work? It works for a very, very simple reason. There are only 3 possible relationships between delta prime and delta. Either delta prime is the greater of these 2 values, or delta is the greater of these 2 values, or both delta prime and delta are the same. So let's assume for now that delta prime is greater than delta. So if this is a, then I can have a minus delta, a plus delta, and since delta prime is greater, this is a minus delta prime and a plus delta prime. So notice that by this definition, I'm gonna ensure that x is a real number that is less than delta, because in this case I've assumed that delta is less than delta prime. That means the x I pick is going to lie in this interval, which of course is also a subset of the it is pretty much chunked between, it is in between a minus delta prime and a plus delta prime. So the x that I pick is actually both within delta and within delta prime of a. The same argument or works if I say that, if I reverse this, if I say that delta prime is less than delta, then in this case this minimum operation is going to be equal to delta prime, and once again my x is going to lie in this interval, and that ensures that the x that I pick is both within delta and within delta prime of a. If both of those are equal, it doesn't really matter. If both of these are equal, no matter if the minimum operation yields delta prime or if it yields delta, any real number I pick is just going to be within delta prime and within delta of a. So that does not matter. That case is rather trivial. Okay. So clearly what I've shown is, or what this choice of delta does is that, so this implies, or what this choice of x does is that it implies that, so 2 things we get from this. The first thing we get is 0 has to be less than, because remember, This ensures that my x is both within delta and within delta prime of a. So the first thing I get is that my x is within, let's say, delta of a. That is this condition right here. So because remember, in order to show that the limit did not exist, I had to show that my x was within delta of a, and I also had to show that the absolute value of f of x minus L was greater than epsilon. So this is the first thing I've shown. So this is as needed. This is the first part. And what I also know is that 0 is less than the absolute value of x minus a, which is less than delta prime. But notice that by 2, I know that if x is within delta prime of a, then f of x has to be greater than L plus epsilon, which implies that f of x minus L is greater than epsilon, but we know epsilon is greater than 0 because epsilon was 1, so it has to be greater than 0. And that implies that the absolute value of f of x minus L is greater than epsilon as needed. And now what I've shown is, say hence, I have shown that 0 is less than the absolute value of x minus a, which is less than delta, and the absolute value of f of x minus L is greater than epsilon as needed. And this completes the proof. So what I've shown through this proof is that if a limit does not exist, sorry, if a limit is infinity, then you can conclude that that limit does not exist. The opposite is not true. I already showed you that there are other ways for a limit to not exist. Like even if a limit is negative infinity, then the limit does not exist. It's pretty much the same proof. There are only a few parts that change, but the underlying point is that if ever you get that the limit is infinity, like let's say that you get a function that looks something like this. Let's say there's a vertical asymptote over here, and you get a function that looks like this. Then, and let's say this asymptote is x equals 2. And someone asks you to compute what is the limit as x approaches 2. I mean, of course, the answer is infinity. Limit as x approaches 2 of this function is infinity. But that also means that the limit as x approaches 2 of this function does not exist. Both of those are correct statements. They are not equivalent statements, but they are correct. Both of those are correct statements. The reason, once again, why they are not equivalent is in order to prove equivalency, you need to say that this implies this, and then you also need to show that this implies this. In this case, if the limit does not exist, then that does not necessarily mean that the limit is infinity. There are other cases in which the limit does not exist. Yep. So yeah, once again, the reason why I chose this theorem is because I asked a couple of high school students. I was discussing a similar question with them, and they were debating about like, I mean, if the limit is infinity, then how can it be that the limit does not exist? I mean, the limit is infinity according to them. So it's actually not the case. I mean, if a limit exists, a limit can only exist if it is actually equal to a real number. It cannot exist if it is infinity or negative infinity. It has to equal a real number, and infinity is not a real number. Thus, the limit does not exist, and this is the rigorous proof for that. So yeah, I hope you enjoyed the video, and yep, I'll see you in the next video.